Hi, everyone. My name is Laurel Bellman. I'm an event manager with the Division of Information Technology, and I am here to welcome you to this great presentation today, Faster, Better, and Cheaper, Refactoring Course Search and Enroll, something that's really important for us at UW-Madison. So presenting the session today is Brian Hill, who is a software engineer in the Enterprise Integrations Unit of AIS, also in the Division of Information Technology, and Ben Nyland, who just closed on a home. But other than that, I don't actually know your title, Ben. Would you mind letting folks know a little bit about what you do?
Yeah, I am a software developer on the road team within Enterprise Integration and AIS, also in Do It, and I work with Brian.
Thank you. All right, folks, if you have any questions or comments for Brian and Ben throughout their presentation, just feel free to pop those into the chat and I'll read those out. Um, Other than that, I'm going to let Ben and Brian take it away.
Hello. There's a saying that when you set out to do an engineering project, you have a choice, fast, cheap, or good. Pick two. However, in our team's recent refactoring of the course search and enroll system, we tried to improve all three. Course Search and Enroll is the website that UW-Madison students use to enroll in classes and manage their enrollments. It was initially deployed on premises in 2016 and moved to AWS in 2017 to handle more traffic. It is very busy during priority enrollment periods, and it's critical that it remain available as it's the only way that students have to enroll in classes. After the initial deployment on premises, we manually provisioned all the AWS infrastructure in the AWS console and used our own scripts to deploy the application Docker containers. We initially had three application tiers in two different AWS regions where the system is deployed. During refactoring, we moved the development tier to its own region. Due to the critical nature of the system, we've generally prioritized reliability and performance over cost savings. The immediate need to refactor was triggered by AWS deprecating a feature that meant we'd have to migrate all the Docker containers to new infrastructure anyway. However, there were many other reasons to do the refactoring work. We'd manually provisioned all the AWS components, meaning there was no overall plan that described our AWS infrastructure. We had to rely on diagrams and notes that we'd made ourselves. Troubleshooting was somewhat difficult, and there was infrastructure that had been provisioned that we'd never used. Docker containers were deployed using the Elastic Container Orchestration System, but on long-lived EC2 VMs that we needed to manually maintain. Adding servers to handle traffic was very slow, since a new EC2 VM takes several minutes to provision. So we kept empty VMs available to each Dockerized service to ensure they could be replaced quickly if needed. However, most of the traffic is during the school day, but without auto scaling, we had to keep enough infrastructure running to handle peaks and surges. During nights and weekends, the system was lightly used, but we had the same number of VMs provisioned at the same cost, running 24/7. Apache and Shib, while popular, are not really well suited to the cloud. You can't remove running instances without forcing users to log out. Apache requires frequent patching manually, and speaking from personal experience, is not entirely reliable under heavy load. Also, there are a number of AWS innovations that have become available after CSE was deployed to the cloud, and we wanted to take advantage of them as we adopted them in our newer projects. Finally, the cost of running the system had become quite high, and we were certain we could reduce it. We had a long list of things we wanted to change. We'll dig into those things in the rest of this presentation. The first was to provision the system components using an infrastructure as code tool called Terraform. This created a map for us to use to troubleshoot and navigate the system as well as eliminate manual deployment errors. We wanted to eliminate Apache and Shibboleth and migrate to CloudFront and OIDC. This moves the web server role that serves pages to users to a managed service that is cheaper and more reliable than a cluster of EC2 VMs for Apache. We also wanted to move from Shibboleth to the more modern OIDC authentication protocol. We wanted to rewrite and refactor some long-running applications into Lambda functions. We also wanted to move from EC2-based Docker deployments to a service called Fargate. Overall, we wanted everything to auto-scale and add servers based on traffic to avoid paying for excess capacity that wouldn't be used. Terraform allows us to create a detailed definition of the infrastructure we want and either creates or updates the actual infrastructure to match the definition. It's very flexible and can work with most cloud services as well as on-premises systems. Terraform lets us preview any changes it will make before applying them so our team can do code review on all infrastructure changes. We preview and apply the plans using GitLab CI/CD tools. The road team has been deploying all of our other applications using Terraform for a number of years, but Core Search and Enroll predated our adoption of Terraform. We started by provisioning duplicate infrastructure in each tier, starting with the development tier. A base infrastructure Terraform plan was the first and created the network components such as VPCs, internet gateways, load balancers. It also included global infrastructure such as IAM policies and S3 buckets. Each of our applications and Lambda functions has its own Terraform plan to deploy that's kept with the application source code. Decomposing the infrastructure into separate plans reduces cognitive load while reviewing them, as well as reducing the scope of potential changes when a Terraform plan is applied. We deployed the same Terraform plan to each tier with changes to regions, service addresses, and cluster sizes between them. By deploying a new parallel system, we were able to fully test it and finally cut over by just swapping the DNS mapping.
As for Apache, Apache containers that we used to run for Core Search ran in ECS as mentioned previously, and that is what we use to serve the website and handle the authentication using the shibboleth module. And that was difficult to scale down, as mentioned previously, due to after traffic spikes because users would get logged out due to sticky sessions. That was just caused because the shibboleth sessions were assigned to individual Apache instances, and so we had to route them to the same one each time to preserve their session. And so scaling down would just log people out. But now we use CloudFront for core search, and that serves the website from an S3 bucket. Um, CloudFront behind the scenes uses Lambda at Edge to handle the OpenID Connect authentication flow, and it does that before the user ever reaches the content of the website. CloudFront also allows for granular caching of static assets, which optimizes load times and also provides other cost-saving benefits because we can add cache control headers on our JavaScript, our CSS, and those apply both at the browser level and at the CloudFront cache. And because of that, we can reduce the bandwidth cost that we pay for in AWS by caching these assets, and it also reduces the latency, the load times for users visiting our website. CloudFront also provides a lot more metrics and visibility into the system's performance, including request counts, error rates for CloudFront, the Lambda handler, S3, all the above, along with access logs. So CloudFront overall is just much more cost efficient as Core Search and Enroll doesn't really have constant traffic. We have our enrollment periods and the students are on during the school day checking their schedules and stuff like that, but it doesn't have a consistent traffic pattern. And so using the pay per request pricing model that CloudFront and Lambda at Edge have is really beneficial for Core Search. Next. So Shibboleth to OpenID Connect. Core Search used to use Shibboleth for its authentication flow, and now we use OpenID Connect, which is just an extension of OAuth 2.0, but it provides identity information, which we need because we need a student's identity to provide the enrollment actions and workflows for students within Core Search. Because of OpenID Connect, our web server is completely stateless. So Shibboleth used to store these session IDs in the user's cookies in their browser, which is what needed sticky sessions. But OpenID Connect, it stores their token, their identity, and then the Lambda handler can verify it each time they attempt to make a request. So servers, backend services can validate these tokens using NetID logins, public keys, and we're able to cache these public keys on server startup, which reduces the request latency for other students that attempt to access those backend services. They can just use the keys that are already in memory and then quickly decode and verify the JWT to then validate the request. OpenID Connect is nice because we have complete transparency and control of the login flow. Shibboleth is just a program, whereas OpenID Connect is a standard. It's not much more than that. We get to implement the standard however we want. And in the case of core search, we have a Lambda function that implements that specification to our needs, and we can add any sort of metrics, logging, any of that we can do ourselves. And we have full control over the code that runs to implement that spec. So core search and enroll uses NemZic is what we call it. It's simply a Terraform module and a GitLab pipeline component for cloud deployment. It acts as a blueprint and it has different input variables you can pass into it. For example, your OpenID Connect, like client ID and secret, and you can pass that in. And it allows for, it's a blueprint that lets multiple different applications, for example, core search, DARS, MAD, which is a diagnostic tool for core search, all those websites use this same blueprint just with different variables. So it's very quick and easy to spin up these websites that have to integrate with NetID login, which is super nice. Next. So bot protection is another cool feature that we have here using the web application firewall in AWS. And this is something that we've seen across the university of bots targeting websites, and Core Search was one of them. So priority enrollment during November 2025, we got a big spike of bots coming in on November 11th. And we can see that on this chart below here, it spiked up to 256,000 requests over the course of about a couple weeks. Students were still able to enroll successfully. It wasn't too much of a disruption because of the serverless nature of Core Search now. Um, but towards the end, on November 23rd, the bot control rule set was applied, specifically with the targeted rule, which completely got rid of the bots because it's able to detect them in many different ways, whether it be user agent headers or just any sort of volumetric data point we have, which in this case, there's a lot of volume and it can block on that. And this successfully mitigated the effect of bots that Core Search saw during the enrollment period, which is a really cool feature that we can have the WAF integration with CloudFront. Next.
As we mentioned, website traffic at UW, including core search, is primarily during the weekday and drops off dramatically at night and on weekends. We wanted to convert as many of our services as possible to serverless Lambda functions so that we're only charged for actual traffic instead of 24 hours a day. Lambda functions are small applications designed to be started quickly in response to requests and shut down when no longer needed. We only get charged when they're actually running. Even during the day, there were some applications that were rarely used. Also, the evolution of the system from its original on-premises deployment left some applications with only one or two endpoints still in use. These could all be replaced by Lambda functions. There were also 5 existing Lambda functions that did little but proxy requests to Apogee to access the DARS API, and we also thought we could simplify that. We migrated one of the PDF generator applications to a Lambda function, but the other we were able to eliminate by having the PDF generated entirely in the browser using TypeScript. We also split a legacy application into 2 separate functions and replaced the remaining functionality with another Lambda function. Finally, we were able to eliminate 5 existing DARS access Lambda functions by enabling users to access Apogee directly with their UW OIDC credentials. We were still left with 3 applications running in Docker containers that we didn't have time to convert to Lambda functions before the next enrollment period. Our Dockerized server applications were initially deployed onto EC2 hosts, which are full-featured VMs, not that different than the ones you can provision on premises at UW. We orchestrate application container changes using an AWS service called Elastic Container Service, or ECS. AWS introduced Fargate as an option for ECS-hosted containers shortly after we launched CS&E. Fargate is a fully managed Docker container hosting service, freeing us from having to patch and maintain the hosts. AWS refers to it as serverless since there's no shell access to the underlying hosts or SSH logins. Adding and removing application servers to handle more traffic is much faster with Fargate than EC2, so there's no need and no ability to provision empty hosts just in case you need them. We updated the application code to authenticate with OIDC instead of Shibboleth, but otherwise use the same Docker container configurations with a different deployment mechanism. So we built the entire system in the development tier, then applied the same Terraform plans to the test tier for functional testing by stakeholders. Then we provisioned and deployed the system to the new hidden production environment to do final testing and get stakeholder approval. We cut over to the new system by simply remapping our public host name to the new CloudFront URLs so there's zero downtime. Finally, we manually deprovisioned the legacy system after we were sure we weren't going to switch back. Building a duplicate system while we were working on it allowed us the freedom to make wideband changes that we could not have made in place with the system that was in use. All of these changes allowed us to reduce our AWS infrastructure considerably. We reduced the number of Docker containers running 24/7 by more than 2/3, and the number of provisioned VMs, including Fargate, by 80%. There were no more VMs running empty in case they're needed, and more of our functionality is handled by managed services. Comparing our busiest month of April enrollment from 2025 to 2026, we reduced AWS costs by 63%. And while most of the savings was from EC2 VMs that were no longer running, there were savings in nearly every service except for a few that we'll describe. The biggest savings was from shutting down EC2 VMs and migrating them to Fargate. Next, we saved a large amount from OpenSearch because in the process of doing the migration, we deprovisioned an Elasticsearch logging stack that was no longer needed. This is another source of cost savings we found during this refactoring, doing a careful inventory of all of our cloud components and eliminating the ones that were no longer needed or used. Finally, we saved quite a bit of money by setting reasonable log expiration dates on our CloudWatch logs, as the costs can add up after several years of busy logging. Some costs went up. Obviously, we weren't using CloudFront before, and we're now paying $142 a month for it. We weren't using the WAF very effectively before the refactoring, and now we are filtering all traffic through it. A lot of this cost on the WAF is from blocking aggressive web scrapers exceeding our rate limits while pulling the public data from the public version of our website that doesn't require logins. Finally, ECS costs went up due to the use of Fargate. Cost savings weren't actually the original rationale for this refactoring. Other benefits we've received from it include we have a detailed plan for all of our infrastructure now that we can use disaster recovery if needed. All infrastructure changes are now previewed and peer-reviewed by the team. CloudFront is noticeably faster than our Apache cluster. Part of that is due to CloudFront's caching abilities. All of our VMs are now auto-patched and managed by AWS. There's no SSH access anywhere. WAF protection stops both the denial of service attacks and aggressive web scrapers. And finally, there are fewer things to break, fewer maintenance tasks to be done, and more services managed by AWS. In conclusion, use Terraform to get control of your infrastructure, CloudFront and OIDC to improve performance and stability, and Lambda and Fargate to reduce costs over EC2 VMs. Overall, set up auto-scaling services on everything that you can. And I think we're ready to take questions.
Thank you, Brian and Ben. That was really, really interesting. Are there any questions in the chat or any comments, thoughts anyone would like to share? Anyone?
Brian and Ben, will you be able to talk a little bit about the tools, the process that you followed to figure out where to optimize from a cost point of view and then maybe resource usage point of view?
I think maybe the first thing we took as I guess an unspoken rule was everything can be a Lambda in theory. And then it was a matter of looking at what was the easiest thing to replace, what was extra, what didn't we need. We had been kind of making a list of things over time. We have one of our releases in Jira is technical debt, and we just stick stuff in there when we think about it, and then during periods like this, we go through it and we pull things out. Um, but the main strategy we used was to try and make everything either auto scalable or basically make everything shut off when we're not using it. And that isn't always possible. We weren't able to make everything like that. But as much as possible, really did make a big difference. I don't know if that answered your question. Ben, did you have anything to add to that?
One thing I found useful in terms of cost for bringing this up has been just looking through and getting familiar with the Cost Explorer, really. And that really came from CloudFront and the whole Lambda OpenID Connect setup that we have, and just being able to see it by, well, not region because it's CloudFront, but like by repository and see what's costing what, and then being able to optimize it um, as effectively as possible. And getting familiar with Cost Explorer has been very helpful, and even with the WAF because it shows the different the rule groups that we have, and then the regions, so you know um, which WAF costs how much because you can see each WAF on the Cost Explorer. So being able to see all those has been really effective for really optimizing the cost.
So, speaking of cost, Ken would like to know if Amazon's costs shot up compared to other clouds, how quickly do you think that you would be able to move over to a second vendor?
Well, we started on-prem. We wouldn't want to go back on-prem because we have so many Lambdas now. But a lot of the Lambdas are also written to be applications. So, and they're fairly generic. We have tied into the AWS APIs to some extent, but not to where it's more than a layer around the outside of the actual business logic. Um, My thought has always been don't worry about platform lock-in too much, as long as you can theoretically move, um, because it takes way longer for UW-Madison to move anything anywhere, like functionally, administratively, legally, than it's going to take us to move a bunch of computer stuff. I mean, if we had to, we could probably move this to a brand new cloud in a couple of weeks, and it's going to take way longer, and we're going to get way more notice ahead of time if suddenly, oh, we have to leave, everyone has to leave Amazon and go to Google or some other cloud or back on-prem. Um, that would hurt more on-prem, but we could do it. I have a plan in mind if it ever happens. I hope it doesn't.
Great question. Um, Joe is curious, are you using a container registry, something like GitLab or AWS?
We put we when we build the images, we're pushing the first copy we do during the before the merge request is approved. We push it back to GitLab under the SHA, the GitLab, the Git checksum, so that's unique. And then that lets us do the security scanning on the container within GitLab using its tools, which is basically free for us. Then when it's time to deploy to Amazon, we deploy to yeah, their Elastic Container Registry. And then we push the exact same image to all of our tiers so that we know it's the one of the problems that we wanted to take care of, we took care of this one a long time ago, was like, is this code the same code that's running on the server, right? That's like an age-old programming problem you just never want to deal with. So we don't. It's always the same image, and it's always the same image in all tiers, unless we're working through a merge request. So yes, we use the one in GitLab before merging, and then the ones in Amazon after merging, because those are the ones we deploy from.
Great. Ken did have a follow-up. He was curious how long you felt like it might take to move stuff, and then what in the local architecture would you miss the most if you had to switch to something different?
Well, Lambdas are just so easy to use. Um, I personally find the API gateway model pretty easy to understand too. I've had some contact with Google's cloud in some private work I do. And I did not like the model as much as it didn't really seem as clear to me. Um, I guess it'd be the lambdas and the API gateways. With a load balancer, I mean, that's pretty cool too. We can do a lot of flexible routing with that. Honestly, it's the load balancer that made all this possible. I mean, from the customer's point of view, it's still the same like website, but behind the scenes, we're able to shift things around by changing where the load balancers point to. So that's another one. They have great load balancers in my experience compared to Google.
Great. Eric had an opinion that he shared that he's hoping that Do It will at some point start providing a platform as a service. Care to weigh in on that opinion?
We tried that before, right? That was CCI, and I don't think it ended up being big enough. Maybe, but if they would, it's going to be hard to approach the level of sophistication and tooling that we have with any other commercial clouds. That would be my concern about that. Um, it's because that I have gotten used to that tooling now. So being able to use APIs to deploy your software and monitor it and do all that stuff. And it's all pretty well trodden. There's a lot of documentation on it. I guess that would be my only concern about going back to a UW platform like that.
Excellent. Anyone else have a question for our presenters? Not hearing anything, which is good because we're pretty much at time. If someone does have a question, feel free to reach out to Brian and Ben. But I want to thank all of you for joining us this afternoon. And of course, a huge thanks to Brian and Ben for sharing all their work with us. I'm sure everybody here has learned a lot from your presentation. So thank you very much.
Thanks.
Yeah, thank you.